Section 7.5 is on integration strategy. In this section, there's not really any new techniques that we're going to learn. It's just a section on looking at integrals and deciding which of the techniques we've learned so far should be applied. So the first thing you need to do is you need to know all your integration formulas. There are the basic ones that come from derivative formulas, and there's a list of those on page 495 in the textbook. This right here is another one that you need to know. This one comes up quite a bit, and so know that one. And then if you don't immediately see which method to use, then the following steps can kind of guide you through it. First thing, you might try simplifying the integrand. If you had this integral, the easiest way to do this is to multiply that e to the x across the 3e to the x plus 5. It turns into this, and then you can integrate both of those easily. All right, cotan x over sine x. What my first thought with this would be to rewrite it in terms of sines and cosines. But if you think about it a little more, cotan on top, and you've got sine on the bottom. So you could rewrite that like this. And 1 over sine is cosecant. And cosecant cotangent like this, that's almost the derivative of cosecant. The derivative of cosecant is negative cosecant cotangent. So you could integrate this and get negative cosecant. This one looks nasty to begin with, but the important thing here is the denominator only has a single term. And when the denominator only has a single term, what you can do is split it into 3 separate fractions. And I went ahead and did the simplification. And then we can just integrate those term by term using the power rule. Next, you'd want to look for an obvious U-substitution, and obvious is kind of subjective there. Some are definitely more obvious than others, but let's look at this. If you had this integral, your first thought might be to use partial fractions on it, but if you let u equal x squared plus x, the denominator, du is going to be just the numerator with dx on it. So you can do that quickly without with u sub and not have to do partial fractions. This one might not be obvious, but if you let u equal cosine, what that'll do is it'll turn this into 1 plus u squared, and then the top and the dx together just become minus du. So it turns into something that you can integrate immediately using the arctan function. And this one, while it's true you could do this one with trig substitution, it's a whole lot easier to do this. If you let u equal what's inside the radical, the du is going to be 8 dx, and so the 2x dx is going to be 1/4 du. Notice what all these things have in common is the numerator is just the derivative of the other function. Down here, well, I guess it's not the derivative of the other function here, but the numerator here is the derivative of cosine, and over here, this is the derivative, or at least a multiple of the derivative of 4x squared plus 5. So if you can do a u sub, go with it, because that's going to be quicker than using partial fractions or using trig sub. All right. After that, if you can't use U-substitution, then you need to classify it and determine which method to use. If it involves trig functions like the stuff from section 7.2, use those methods. And, you know, those methods were mostly identities and U-substitution. If it's a rational function, then try partial fractions. If it involves a product, you might want to try integration by parts. And if it involves these sorts of radicals, where you've got a squared plus or minus u squared, or the other way around, and if that shows up, you might want to try trig substitution. Even if the radical isn't there, sometimes trig substitution is still the thing to do. And also, if you had u squared plus a squared in parentheses raised to like the 3/2, that 3/2 is kind of like a radical, because it's, you know, raising it to it's taking the square root and cubing it. So trig sub is good to use on those things. All right. If classifying the thing fails and you're still not sure what to do with it, then we're in sort of more shaky territory. Don't expect much of this to show up on the test. Most of the stuff on the test you'll be able to identify, I think. But if all that fails, you might want to try a non-obvious substitution. You might want to try integration by parts, even if there's not a product in the integrand. That can especially be helpful if you have something like integral of natural log of x, or if you have integral of one of the inverse trig functions. You might try using multiple methods together. We saw a few things where you'd use U-Substitution, and then after that you'd use integration by parts. And you might want to try manipulating the integrand again. All right. If none of that stuff works for you, then at this point it's time to start looking for some help. You can try looking in the tables in the back of the book. They have a lot of forms where they basically worked out integrals for you. You might try plugging it into Maple or Mathematica or into Wolfram Alpha or any other online type thing that can do this for you. Those are good for checking answers, but you need to be careful with those because sometimes they do weird things with simplifying, and sometimes they use methods that are different from what we've done, like maybe hyperbolic trig substitution or something like that. So sometimes they'll give you an answer that's correct, but it looks very different from what you'd expect. And as a last desperate resort, you just have to give up. Unfortunately, some integrals are hard. Well, that part's obvious. But some are even impossible to do using elementary functions. Like this one right here, integral of e to the x squared dx. It's impossible to do that using elementary functions. You have to use what's called special functions, which is like advanced calculus. Notice if there were an x here between the between the integral symbol and the e to the x squared, this thing would be easy because you could just let u equal x squared. But there's no x there, so it's impossible. If you're interested in that, page 498 has a good write-up about it.